All right, welcome class to the penultimate lecture of the semester, lecture 27. We are going to continue our discussion of Landau's theory of phase transitions, shifting our focus mostly through this lecture to the topic of first order transitions. Transitions we have more common experience with, things like condensation or freezing. Those are both examples of first order transitions where there's an abrupt change of an order parameter, not a continuous change of an order parameter like we see in second order transitions. So we have two specific things on the agenda. The first is to flesh out a little bit more a relationship alluded to last lecture between the Landau approximation to the correlation function and a non-local response function, the non-local susceptibility. So we'll derive that relationship for our Ising magnet. And then we will turn our attention to a liquid vapor transition, first showing how it is that within Landau theory, it is equivalent to our phi-4 field theory for the magnetization transition. That involves working along a symmetry line, a particular line where the liquid and vapor are equally likely. The filled and unfilled states of the lattice gas, if you remember all the way back to a lattice discretization of the system, where those are equally likely to be, which is a manifestation of the same sort of symmetry group that the Ising magnet falls into, a certain so-called Z2 symmetry group. Then we will generalize our discussion of first order transitions a little bit more. And the last lecture, lecture 28, will really focus more on that specific topic of first order transitions, work out some basic properties and scaling relationships, and then work out a couple of concrete examples. Before we do either of those, though, let's review just a little bit. So we have been working with a so-called phi-4 field theory. This is a Landau theory for an Ising model, a theory for second order transitions where you have a scalar order parameter. E.g., it could be like the local magnetization, or we'll show later, it could be like the local density. It is a scalar in that it is a one component field. It has only extent, not direction, like one might need if you were talking about a ordering of a dipolar field or spins that can point in more than just one direction. For that scalar order parameter, we have argued that an effective description of its fluctuations can be written as a sum of a local free energy and a so-called squared gradient term. This local free energy density is some low order expansion in the field for something with even symmetry. This is an even order polynomial. This squared gradient term penalizes inhomogeneous fields, so fields with structure to them that aren't just constants through space. Typically, all of these parameters are determined phenomenologically, and A, for example, is endowed typically with a temperature dependence. Some constant C times little t, where little t is the temperature less its critical value. And all the other coefficients, so C U, gamma, sometimes I've written it as M, are all positive numbers. We discussed a little bit of this in the small groups last week, that if U, for example, was not a positive number, the free energy could be minimized arbitrarily by increasing the field as large as it could go. So the field would become unbounded, which is not physical. So U, to truncate at fourth order, U needs to be positive. Similarly, gamma needs to be positive. Otherwise, the system would favor forming interfaces, and thus ordered states would never be stable. So gamma, like a surface tension, is penalizing interface formation, fields with gradient contributions, and thus in order to stabilize interfaces, gamma need be positive. And we have worked out a number of consequences of this theory. For example, at the mean field level, the average value of phi in the absence of boundary conditions that act to make it spatially inhomogeneous or applied fields that have itself structure. It is a constant through space, which is 0 if t is greater than 0, so you're above the critical point, and exhibits spontaneous symmetry breaking with two degenerate solutions for temperatures less than the critical point. Exactly what we would hope for in our phenomenological understanding of an Ising magnet. We also have worked out non-trivial exponents. So this is this 1/2 is known as beta. It's a critical exponent for how the order parameter varies as a function of temperature in the vicinity of the critical point. We've also worked out non-trivial aspects of the field, like its correlation function. In 3 dimensions, this correlation function is exponentially decaying with a correlation length, has a 1/r component, and has a constant out in front. This characteristic length scale depends on both the parameters that we've put into our Hamiltonian. Almost from dimensional analysis, you can anticipate what should dictate that length scale. The difference in the coefficients C, U, and gamma. Well, gamma has to have a different set of length units than C or U because it enters in as that squared gradient term. And indeed, this length scale C is equal to a simple ratio of gamma over CT square root of, when t is greater than 0, and something very similar, gamma over -2 CT to the 1/2 in the ordered state. This tells you that this correlation length, this characteristic decay, of course chi being how the fluctuations in the field are correlated in space. This tells you that that correlation length is a result of a tension between the energy scales to generate inhomogeneities and the characteristic thermal scale for fluctuations, which are local. Those are fluctuations that are about the minima, as characterized by just the second derivative of the free energy with respect to the field. Exactly at the critical point, this length scale gets infinitely large. So when t is equal to 0, and the correlations, rather than decaying exponentially, decay with the power law, are so-called scale-free. This is what gives rise to the complexity and scale invariance of a system at its critical point. Using this information of the correlation function, we have argued that if we try to make fluctuation corrections to our mean field theory, we actually can never win in the dimensions that we care about. Fluctuations always become a non-negligible contribution to the partition function or the free energy if we get arbitrarily close to the critical point. Though, how close we can get depends on microscopic parameters like the characteristic Bayer correlation length, so how the system is correlated away from its critical point, as well as thermodynamic quantities like its energy density as codified in the heat capacity. And for many systems, actually, mean field theory holds pretty close to the critical point. For systems with very large Bayer correlation lengths, like superconductors, this is exceedingly true. Okay, that's about all I wanted to review. Let's go ahead and focus back on this correlation function we've just written down and actually demonstrate that it is a so-called non-local susceptibility, that it tells us how, if we turn on an applied field at one point in space, how that affects the value of the order parameter field at another point. This will be kind of our last little calculation, more for completeness of our regular old 5-4 field theory before we move on to first order transitions. So as before, we've written down our effective Hamiltonian with this local free energy density and squared gradient term. We could add to that Hamiltonian an applied field, the associated partition function in the presence of the field would be an integral over all possible fields weighted by our effective Hamiltonian, which depends on that value of the field. And in the presence of an external field that might itself vary through space, we'd have this additional term. So this is the partition function in the presence of H. Now, we've seen this sort of structure a lot where when we look at a partition function with some Hamiltonian that we are most interested in, along the symmetry line in this case, and we add something linear or linearly conjugated to our fluctuating variable, in this case, the field. You all know that there's a trick we can do, which is to rewrite this as a product of a partition function in the absence of the field and an expectation value over the exponential of just that field times our order parameter, averaged in the absence of the field. This is useful because it reminds us that this partition function, QH, is a generating function. Namely, if I took a derivative of log of QH functionally with respect to the field at one point, I then set the field equal to 0, I will generate the cumulants of the field. The first of which is just the average value of the order parameter as a function of space. The second of which, if I took two derivatives of QH at a field at point R and with respect to a field point at R prime, this is then the correlation function of phi at R and R prime. This is what we have defined as our chi throughout this course. Note that this is also how the average value of phi changes with a perturbation of an external field at R prime. This is why people often refer to chi as the non-local susceptibility, because it tells you how the order parameter field phi is susceptible to a perturbation non-locally over at position R prime. Now, if we actually wanted equations that would let us compute these variables, average of phi or the non-local susceptibility, our correlation function, we can run back to mean field theory. We know that at the mean field level, in the presence of some external field, the value of the field that minimizes the free energy will be the one that contributes the most to the partition function. So if we took a derivative of the argument of our exponential, all of this here, and minimize that, that would give us the value of the field which most contributes to the partition function, gives us an equation that we could try to solve in order to evaluate the mean of phi. We've written down this before. It's a so-called Euler-Lagrange equation. Inserting what we mean for the Hamiltonian, we'd have a term A of t, a single value of the average field at R, a u times that average cubed minus gamma, two gradients of that average, and that would all be equal to that external field. So in the presence of that external field that depends in space, we lose the translational symmetry. We can find solutions that depend on the specific spatial location we're looking at. We have largely solved this in the absence of an external field, where we know that spatial dependence vanishes, and thus the squared gradient vanishes. This equation also gives us an equation for computing our non-local susceptibility, our correlation function. If we took this relationship seriously, we need only compute another derivative with respect to h in order to arrive at that equation for the susceptibility. So these averages depend on h. But that is the same dependencies right here. So if we took a derivative of this equation, both sides of this equation with respect to h, over on the right-hand side, that's just going to be a delta function. on the left-hand side, I will get a constant, and the derivative of phi with respect to h is what I mean by chi. The derivative of phi cubed with respect to h, well, that will give me a u, a 2 factors of phi at r, and then a factor of chi through the chain rule. And now our squared gradient term, well, I can commute the functional derivative of h with the spatial gradient and thus just get chi underneath that gradient. So this is interesting because it is an explicit equation that if we could solve, it's an ODE, that if we could solve it, we could get chi. It clarifies another perspective on what exactly chi is, which is a so-called 2-point Green's function. It's the response of the field to a point source. That point source is, right here. I put a point source and I ask for how the field responds at a distance r prime to that point source. This ODE is actually not so complicated. Fourier transforming it, we would get a of t, some chi hat of q, plus these are just numbers. The 2 gradients will bring down 2 factors of q, get chi back. The Fourier transform of the delta function is just unity. So now I have an algebraic equation that I could rearrange and solve for chi, leaving me with a of t plus 3u, the magnitude of the average value, plus gamma q squared. To put it in the form we've seen before, I can take a 1/2 magnitude of a 1 plus chi c squared q squared, noting that average of phi is 0 for t greater than 0 or minus ct for t less than 0. And identifying again this correlation length as gamma over twice a of t. Square root of. So the susceptibility, so viewed in terms of correlations and response, this tells us that the susceptibility, the most permissive mode, the mode that if we push on, if we perturb with a field, that we will get the largest response, is the value near q is equal to 0. So macroscopically, if we're near the critical point, so this chi is strongly peaked at q is equal to 0. So if we were to plot this for chi or c large, we'd find something like that. So the dominant contribution to the susceptibility in the vicinity of the critical point where the characteristic correlation length is large is a macroscopic response. This is very different from the sorts of things we saw in the first part of this class, where that correlation length was, or that correlation function, the susceptibility, was peaked at microscopic length scales. The peak in the structure factor, so the density-density correlation function, is at 2 pi over the diameter of a molecule, not at the macroscopic length scales, the size of the container the system is in. Okay, so that was just one last little calculation I wanted to do with our 5-4 field theory, showing you some things you might run into in the literature. It's different names for this chi function as a non-local susceptibility, or the 2-point Green's function. If you see equations like this ODE for chi resulting from a point source, now you know where they come from. All right, with that little bit of bookkeeping out, I want to turn our attention away from magnets to show how exactly we can use Landau theory to discuss a liquid vapor transition. So we know a bit of that phenomenology. We know that if we are working at low temperatures, that typically we can take a fluid, maybe like water, and find conditions in which its liquid, its high density state, is in coexistence with its vapor, its low density state. We also know that if we increase that temperature above some critical point, that distinction between the liquid and its vapor goes away. So above here, there is no meaningful distinction between a liquid and its vapor. The order parameter, the fundamental quantity that distinguishes the liquid of the vapor, is thus this density. So if we wanted to use Landau theory to give us some insight into the liquid vapor transition, both its critical point as well as potentially the first order transition that I can find as I condense a liquid into its vapor, or vice versa, or maybe even how to think about this coexistence state where the liquid is in contact with its vapor, we could in principle begin microscopically, take a specific model like a Lennard-Jones potential, try to coarse grain it like we did our Ising model. This would be complete with some low energy, some gradient expansion in the density field and some low order expansion in the density. Or we can operate more phenomenologically by taking the lessons we've just learned in the context of magnetization and seeing if we could just write down a theory that can describe it. So we will operate phenomenologically. There are good books like Nigel Goldenfeld's Theory of Critical Phenomena, which goes through the microscopic route that if you're really interested, you can go and look at. Phenomenologically, we'll imagine that because rho is the important order parameter that distinguishes a liquid and its vapor, we will write down an effective theory that tells us about the fluctuations in the density field. Again, coarse-grained over microscopic dimensions, looking at the density field on a length scale which is large relative to individual atoms and molecules. And taking a cue from what we've done thus far, we can envision that effective description will have a local free energy density piece, something that would know that potentially there are stable states associated with a high density state like a liquid and a low density state like a vapor, and analogously performing some gradient expansion, we might imagine penalizing inhomogeneous density fields with a square gradient term. Now so there's not a lot of room in the square gradient. We could in principle go to higher order gradient expansions, but we won't for the time being. Where we're left with some flexibility is what this local free energy density should be. So remember how we arrived at this in the Ising model in the case of magnetization. We imagined that in the vicinity of the critical point, the average magnetization was small. We then did a Taylor expansion and eliminated terms that would violate symmetry in the absence of an external field. And thus we are left with an even order expansion in M. The density is not even. Even in the vicinity of its critical point, 1 is not 0 if I square it. So there's no reason that an expansion in the density need be simple, need be only even, only have a few terms. Very generically, we should expect that there is a first order piece. There could also be a second order piece. Now we kind of know that stopping at second order is not going to be sufficient because that would be a Gaussian theory. There would be no nonlinear responses there. So maybe we need to go to third order. Third order is also not sufficient. If I was to look at a cubic polynomial, as rho gets really big, if W is negative, that free energy would diverge off to plus infinite rho. That's not very physical. If W was positive, that would be a monotonically increasing free energy. There'd be no ability to have a second stable state. So if we add in a fourth order term, that can turn around and now we have a stable minima at low density and a stable minima at high density. So presumably, provided those two coefficients are positive, we'll be able to describe a transition between a low density state where there's a minima near rho is equal to 0 and a high density state where there's a minima at finite rho. So on its face, this certainly doesn't look like our phi-4 field theory. It does not look isomorphic to the theory we had for magnetization, which is peculiar because we started this discussion of phase transitions noting that universality between liquid vapor transitions and demagnetization transitions. So let's see how we can uncover that relationship. Let's take rho to be some critical value of rho plus some deviation from that critical value. So looking at our phase diagram here, we can take this value of rho at the critical point and then ask, well, how do the coexistence densities change as a function of temperature relative to that critical point? If we plug that in to our local free energy density, that's just a substitution. Can you hear the bell tolling? I'm actually on campus recording this lecture. It's very exciting. All right, like so. That's just a substitution. I can rewrite this if I expand all of those coefficients. If I expand all of those polynomials, remember, rho c is just a number. So let's actually be a little bit more careful. So imagine that that's a fluctuating variable. That's a fluctuating variable. Rho c is just a number. I can expand those polynomials and regroup terms with increasing order of the fluctuating variable delta rho. I will get one term, which is a constant, a next order term, h tilde, which will depend on rho c, but is just a number, not a fluctuating variable, times delta rho. Analogously, I will get some new a coefficient that depends on rho c, and that is multiplying delta rho squared. Similarly, like so. So what are those coefficients? So this c, this constant term, we don't care about. Let's just get rid of it. That's just renaming our zero of energy. It doesn't change with different field configurations, so it really is irrelevant. H tilde of rho c is a number that depends on our original field, a times rho c plus w rho c squared minus u rho c cubed. A tilde of rho c is something that goes like a minus twice w rho c plus 3u rho c squared. W tilde of rho c, 3u rho c less w. And u tilde of rho c is just u. So now, if we inspect these new coefficients, these are new numbers. They've taken our original parameters, which again, were just phenomenological numbers we put in, and they've shifted them around. They've added some function of rho c. What is clear from this analysis is how to choose, or what the value of rho c must be and h in order for these odd order coefficients to vanish. So for h tilde and w tilde to vanish, which if they did, those are this, this term and this term. If those, oops, sorry, wrong line. That's this term and this term. If those two terms vanish and we renamed delta rho phi, that would be our usual phi 4 field theory. It'd be isomorphic with our theory of magnetization. So what is required to do that is that H must equal A rho C plus W rho C squared plus U rho C cubed. So there is some linear applied field that depends on rho C, that if we set to this value, this function of rho c, we will eliminate that linear bias favoring a liquid from its vapor. If we pick W such that it is equal to 3u rho c, that will eliminate that third order coefficient, which is the same as saying that rho c is W over 3u. Substituting rho c back into the equation for H, we can get an equation for H that just depends on, that's closed. It doesn't depend on rho c. Rho c is then thus a prediction or is a result of these expansion coefficients. So plugging in rho c to A tilde in those two places there, we would get a local free energy density as a function of delta rho, which is equal to some A hat over 2 delta rho squared plus U delta rho to the 4th, where this A hat is A less than, so you get 2W squared over 3U, 3W. So this will result in just W squared over 3U. There we go. Just like our 5-4 field theory. So indeed, it follows immediately. All of the results for our discussion of the Ising model can now be applied to this liquid vapor transition. For example, we immediately know what the average value of delta phi or delta rho is. If you go back up to the top of this lecture, you'll see that this is 0 if A hat is greater than 0, and it is plus or minus square root of minus A hat over U if A hat is less than 0, meaning that rho liquid is rho C plus, that's the dense state, minus A hat over U. Rho vapor is rho C minus. So there's our coexistence densities. So if we wanted to parameterize this coexistence curve, for example, we might expand A hat as a function of the temperature. And that would predict a coexistence curve that was of the form of a square root of the temperature that deviated away from its critical point, like T less Tc to the 1/2. Liquid vapor transitions can be modulated with pressure. You can imagine parameterizing this H tilde and thus rho C as a function of pressure as well. Now, what is useful in the context of a liquid vapor transition, so we essentially have all of the critical behavior. We know that we can go, mean field theory will work kind of. What is an interesting calculation to do in the context of liquid vapor transition that we hadn't done in our magnet is to actually ask about this coexistence state. What does the system actually look like what does Landau theory predict the system to look like when I actually put a liquid in contact with its vapor below the critical point? So we can imagine working under conditions of coexistence where our liquid is in contact with our vapor. So this is some high density state. And on the right, some low density state. For T less than Tc, we should expect to be able to form that interface and for that interface to be stable. If we call this direction Z, what do we expect rho Z to look like? So it will have some typical liquid value deep into this liquid state. It will have some typical vapor value, quite small, deep into the vapor state, but how does it go between them? Is it linearly varying? Is it oscillatory? What does it look like? So we can answer this question in Landau theory by actually dealing with our Euler-Lagrange equations and imposing those boundary conditions. So if we went back here, we know that now our liquid vapor transition theory is isomorphic to our phi-4 field theory. So if we just replace this with a hat, we're working under coexistence conditions, so there's no applied field. And instead of calling this phi, I now call this delta rho. The inhomogeneity is along the z direction. We're going to imagine that it's isotropic in the plane orthogonal to z, so in x and y. So the only variation is in z. So we can jump immediately to this result. So the density profile is given by the solution of this Euler-Lagrange equation, at least at mean field. With the boundary conditions that delta, that rho at z far away from any interface is equal to rho L. And rho deep into the vapor state is rho V. So it's a second order differential equation. We require two boundary conditions, and there they are. And those rhos are, of course, known. Those coexistence densities are given just in terms of A and U. Okay. So this equation looks a little scary. It's a nonlinear equation because of that delta rho cube term. Not really lots of good strategies for solving nonlinear equations, other than guessing. At least that's how I would do it. So we know we have approximated the spatially varying terms with just a gradient. That has assumed that only long wavelength variations are permissible. So a reasonable expectation is what I've drawn here, something that smoothly varies between the liquid and its vapor. Now, there will need to be some characteristic scale over which that interface varies, and let's call that scale delta. So if I was going to write down a functional form that looks like that curve, what kind of functional form does that look like? So you might guess an error function. Well, that's going to be a little bit complicated to work with. A reasonable alternative that also looks like an error function would be a hyperbolic tangent. So let's see if that solution is a valid solution. Let's see if that form satisfies our Euler Lagrange equation. So it will asymptote to the right value. It's consistent with our boundary conditions. But is it consistent with this equation here? So to check that, we need to see if we can rearrange this and see if we take two derivatives of that function, in this case our hyperbolic tangent, if it's equal, or under what conditions could it be equal to a sum of that function times a plus that function cubed times u. So two derivatives of hyperbolic tangent z over delta times gamma. Well, the first derivative of hyperbolic tangent, so these factors are just constants, so they just come out. First derivative will pull out a factor of 1 over delta, and the first derivative of hyperbolic tangent is 1 minus hyperbolic tangent squared. The derivative of hyperbolic tangent squared can be written as, give me a factor of 2. I pull out another factor of delta. I get a hyperbolic tangent and 1 minus hyperbolic tangent squared. Like so. All right, that's the right-hand side of our Euler Lagrange equations. Our left-hand side, I can pull out one common factor of hyperbolic tangent. That gives me a of t plus u get 2 factors of that and 2 factors of hyperbolic tangent. Now, if we choose delta rho to be those coexistence densities, square root of minus A over U. We can substitute that back in here. I don't know why I keep putting those moduli everywhere. So putting that in, I will get in, can pull an A out. I have 1 minus, the u's cancel, so I'm left with just hyperbolic tangent squared z over delta. Right, hyperbolic tangent. And that must be equal to our two derivatives. So let's pull this down here. All right, let's see what we can cross out. So we have a factor of 1 minus hyperbolic tangent squared, that's common. Factor of tan h, that's common. Factor of delta rho, which is common. Indeed, this works out provided we choose delta to be minus twice gamma over A. Or that delta is square root of twice gamma over A. And remember, these are all 8 hats. Sorry about that. And remember, A hat is negative in order to stabilize our liquid state, or the coexistence state. So indeed, we found that this hyperbolic tangent is is what Landau theory would predict to be the interface between a liquid and its vapor. It's smoothly varying as a consequence of the gradient expansion. And it has a characteristic length scale, delta, which is twice gamma over A, which just so happens to be twice the bare correlation length. So indeed, there's a single length scale in some sense of this theory, which is the correlation length, parameterized by the ratio of gamma over A. And that correlation length then sets the width of that interface. So as we approach the critical point, so at very low temperatures, that correlation length is small. As we increase the temperature, that correlation length will grow. At the critical temperature, that interface would become infinitely big. Indeed, at criticality, there's no meaningful distinction between the liquid and its vapor. So there should not be a meaningful interface that separates the two. An interesting calculation we can do with this profile is to note that the added energy associated with forming an inhomogeneous system, this squared gradient, has a thermodynamic interpretation. So from our Landau theory, that excess free energy is that squared gradient term. If I ask for that energy per unit area of the interface, this is exactly what I mean thermodynamically by the surface tension. The surface tension is the reversible work to form an interface, and at coexistence, the free energy for the liquid and the vapor is identical. So the only additional cost we pay for putting them actually in contact with each other is the squared gradient piece. From knowledge of the profile, we can work out what Landau theory would predict to be the surface tension. That is gamma by 2, putting in our hyperbolic tangent, we would get factors of average rho, delta rho quantity squared. We'd have an integral over z. Like so. We can take the derivative and squaring that, get 2 factors of delta out. Derivative of tangent can be written as hyperbolic secant squared. Squaring that gives us hyperbolic secant to the 4th. And that's actually an integral one can do. If you integrate over all space, hyperbolic secant gives you twice gamma over 3 delta, like so. Writing that in terms of our A's and U's, this is twice gamma square root of 3u a hat to the 3 halves. As A goes to 0, as we approach the critical point, our surface tension goes to 0. It does so with a critical exponent, in this case 3 halves. Another observation is that this surface tension is inversely proportional to the width of the interface. It's also a useful scaling relationship to keep in the back of your mind. As the interface, as the surface tension becomes very large, the width of an interface gets really small. So nearly miscible liquids, which have very low surface tensions, will have huge fluctuations of their interfaces. The width of the interface will be very large. Solids in contact with their vapors have very high surface tensions, and correspondingly, the interfaces are very sharp. Solids in contact with other solids also have very high surface tensions and very thin interfaces. As we approach the critical point, a way to understand how the surface tension goes away is that the width diverges. The surface tension going like 1 over that width then also goes to 0. All right, so that's liquid vapor transitions. We essentially have solved everything we would want to know about them by mapping them to the theory we already know how to work with, our phi-4 field theory. So let's end the last few minutes discussing first order transitions more generally. So the distinction between a first order transition and a second order transition can be thought of as how the order parameter changes with some control parameter, like the temperature. At a second order transition, like the critical point, we go from the disordered state, a state in which the order parameter is 0, to something which continuously increases, though with a kink. A first order transition is one in which at high temperature, the disordered state has 0 value of the order parameter, but will change abruptly, discontinuously at that transition point. So viewed in the context of Landau theory, this is the fundamental difference. That is, we tune a parameter, either the order parameter jumps discontinuously or it increases continuously. If we wanted to describe such with a simple effective theory, the simplest one we could use, again, we'll have the same form as what we've been working with. We'll have some local free energy density and to lowest order, some squared gradient term. But now this local free energy density needs to be able to describe that abrupt change, that change of stability. So the simplest functional form that can do that is what we've actually already seen in the context of our liquid vapor transition. Moving off of the symmetry line, this fourth order polynomial with a cubic term, cubic because the ordered and disordered states don't have the same symmetry. There's not an up-down symmetry in a first order transition. So that third order term need not be 0. The linear term, we can always roll into an effective third order term, as we've kind of shown in the liquid vapor transition. So this is really the simplest theory. If we're trying to describe a temperature-driven first order transition, we can take that linear or that quadratic coefficient A and provide it with a temperature dependence about some reference temperature Ts. And assume that all of these coefficients, C, W, U, and gamma, are all positive. If we were going to treat this theory, cubic order polynomial, without moving on some symmetry line and treat it at mean field, we could arrive at the average value of phi through minimizing the Hamiltonian. In this case, again, absent boundary conditions or external fields that break spatial symmetries, a uniform state will be most stable, and that uniform state would satisfy a cubic equation of the form like so. Cubic polynomials have generally closed solutions, and indeed this one can be solved. The average value of phi is either 0, that should be clear, there's a common phi everywhere, Or if I factor out one of those phi's, I have a quadratic equation. We all know how to solve quadratic equations. That would give me 3w over 4, right, 8u, plus or minus 9w squared, 64 u squared less twice, like so. So I have cubic polynomial. I have in general 3 solutions. Which one is stable? Instead of depending on the, in some sense is the same as how we decided how one could decide what was stable in the Ising model. You can look for where the solutions go from being real to imaginary. In this case, one could define the argument of this exponent, the argument of this square root, as a so-called discriminant. When that discriminant changes sign, we will change the number of possible solutions. If we just plotted this free energy function, though, we can get some sense as to what this will look like. We can anticipate what these 3 solutions mean. Remember, omega and u are positive. A is what we're tuning to drive a transition. So for A positive, and very much so, I will increase, I might have some little bump for the minus u, but I will keep increasing. Eventually u will dominate. If A is very negative, well, I will decrease initially, decrease even more due to the cubic term, but eventually positive u will win out. So I already see that there is a possibility of having a stable state at phi 0 and a free energy minima at finite phi. What happens in between? Well, I could have A increasing, W big enough relative to it that I have a metastable state. This cubic or this 4th order polynomial could also then have a bistable state if A, W, and U were all finely tuned for that to happen. So the 3 solutions, I think, become apparent. There are multiple cases where the first derivative can be 0, either because you have a stable state or because you have a local maxima. So the ordered state is going to be the one in which we take the positive root, not the negative root. The negative root is essentially monitoring where this maxima is located. So if you were to plot mean phi, as A varies, we follow a path like that. So as a function of t, we will indeed have a disordered state when A is very positive, so t is much greater than ts. But note, when we get to this point, we arrive at coexistence. This barrier is still finite. We will jump discontinuously to this value in the ordered state. And then that value, I've not drawn this very well. It's, as it goes further into the negative regime, its value will shift to the right. We actually know that because as a is negative and gets larger, phi will increase like the square root of a. So note, a seemingly innocent change, just the addition of this finite cubic term, just finding that W is finite, which required that there was no apparent symmetry in phi, or no hidden symmetry if we rearrange our variables. By just having that cubic order term, we now derive phenomenologically very distinct sort of behavior. Instead of continuously increasing our order parameter going through a second order transition, we proceed discontinuously observing a first order transition. So in the final lecture, lecture 28, we'll describe a little bit more about what sorts of order parameters one might choose for first order transitions. These are usually associated with the breaking of a continuous symmetry. We'll talk about different sorts of behaviors that arise when one thinks about continuous symmetries, specifically the sorts of modes, low energy excitations that can arise, so-called Goldstone modes, excuse me. And we'll work out a concrete example of a continuous symmetry or an ordering that happens at a finite wave vector, in which mean field theory and the symmetry of the effective theory would make it seem like it's potentially a second order transition, but fluctuations actually fundamentally alter the nature of that transition, turning it into a first order transition, so-called fluctuation induced first order transition. And that's all we'll get to. So that'll be the final lecture. That'll conclude our discussion of Landau theory and all of our discussion on the advanced course in statistical mechanics. So look forward to that last lecture. I'll look forward to talking to all of you in small groups. I hope you all stay safe and be well.